would like to introduce Errol Roberts, who will be presenting Wavelength Services Delivered Another Way. Errol is a distinguished architect at Cisco Systems and is coming on to us today from New York. This is Errol's first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Errol.
Thank you. So with being the newbie, I hope you guys would be light on me. So Wavelength Services Delivered Another Way. So the whole idea here is really to look at how can we provide dedicated private line services with a different approach. Not necessarily writing a multiplexer or wavelength, but certainly looking at the massive capacity that's available within our routing infrastructure, and taking advantage of the advancement in really the high capacity, the higher interface data rates, and also just a different architecture that you guys may be exploring. So let's take a look at the market landscape. Certainly when we think about high capacity wavelength services, we're thinking about anything over 10 gigabits here in this case, and typically the service would be point-to-point. It would be committed. There's a dedicated set of resources, so typically you'll dedicate it, whether it be some Muxponder, some transponder, there's going to be dedicated set of resources for that particular connection, for that particular customer that you're serving. And typically, there's organizational requirements as well. And typically what we see, certainly within large enterprises as well, is really more a way to have own set of services for different enterprises. If you're a service provider, there may be different groups within the environments that are looking for their own dedicated set of services and dedicated set of connections to meet a particular business need. So when we think about private line service, there's certainly a set of characteristics that we need to think about. Most importantly, it needs to be predictable, guaranteed bandwidth, and you'd certainly want to have some level of protection. And certainly not in all cases, but certainly you want to have 50 millisecond capability from a protection point of view. More importantly, it's going to be bit transparent. So it's a transparent service, so therefore allowing you to carry whatever traffic type you want to carry across that infrastructure. Certainly you want to be able to have all the performance monitoring characteristics of fault detection, and at the same time, you want to be looking for the lowest cost per bit. Certainly cost is always a factor, so therefore how you deliver the services from a cost effectiveness is certainly going to be important and something that would be considered. So typical use cases would be, an easy one would be interconnecting your routing and switching infrastructure. So the customer just want to connect their devices independent of what's happening within the service provider infrastructure. So fully transparent, if you will, so therefore being able to see clearly across that optical connection. So in the case of a router, it can have all the peering and all the adjacencies. If you want to pass MACsec or any other those other types of protocols, you have the ability to do so without any challenges. Certainly there will be data center use cases as well, right? So this may be for data center interconnect. So you may be having lots of links between your data centers, but not only would you be carrying dedicated Ethernet connections between your data centers, you may be also be carrying non-traditional Ethernet type services like Fiber Channel as an example. So you're going to be having these set of dedicated services that's there. And that's typically there today for a lot of customers that we see. And certainly you'll also see just cloud connectivity, whether you're moving from your private data center going out to a carrier neutral facility, or you want to be connecting up into your cloud or your SaaS provider, there's more and more need for dedicated connectivity. And that's just a sample. I'm sure you have other use cases that says, hey, look, there's use cases for dedicated connections. Now, typically, how is this connection delivered today? So if I have a DWDM transport network infrastructure, I may be leveraging a transponder or Muxponder to aggregate, let's say, multiple 10 gigs or multiple different services, point-to-point between any two locations. Certainly, as your infrastructure becomes, or the network topology becomes larger and you want to serve more customers or different groups, certainly you may want to have a much more sophisticated DWDM infrastructure typically that may be built on ROADMs, but you're still delivering a point-to-point service across that infrastructure. And as you look at the service mix and where you're dropping your services off, you may be potentially looking at some electrical switching from an OTN perspective to make sure you're maximizing the wavelength usage across that transport infrastructure. Certainly, as you look at leveraging your OTN capacity, your OTN switches, and certainly you want to be mindful of the capacity of that particular device and then the amount of services that you be carrying and deploying across the infrastructure. What has happened since as we look at wavelength services? Certainly, when we think about the previous graph, when we think about the electrical capacity of your SONET or OTN type devices, we see where the capacity of those devices has not grown over the years, right? You see where you're under 2 terabits in terms of capacity. But if you look at a routing architecture or routing device equivalently, you see where the NPUs today, the network processing units today, are massive scale, massive capacity, right? So if you think about what's on the market today, you'll see a 12.8 terabit switch or a 12.8 terabit NPU. You may see a 25 terabit NPU, and you may see coming along the line, in some cases, a 50 terabit NPU, and it continues to scale. What you're also seeing is really a mix of interfaces on those routing devices, whether it be 10 gig, 25 gig, 40 gig, 50, 100, 400 gigabits. And you're also seeing a flexibility in form factor of these devices. So you can get a small pizza box all the way ranging to a multi-terabit systems. What's the takeaway there? The takeaway there is massive capacity on your switching or routing infrastructure side as compared to the capacity that you define normally within your OTN electrical switching infrastructure. So how can we maximize this capacity that's there, and how can we deliver wavelength services in a different way, right? Providing that point-to-point connectivity with dedicated resources across the infrastructure. Certainly what we want to do is really look at the picture on the left to your right, if you will. And what we'd like to do is be able to aggregate all the different service types onto a particular routing infrastructure, a routing platform, taking advantage of those higher performing digital coherent optics that allows you to connect into your optical transmission system, your open line system. So certainly, I think there was a talk earlier today about ZR and ZR Plus. You may imagine then taking your coherent transceiver, if you will, plug it into those 400 gig ports on your routing infrastructure, and then at the same time have the client ports be any types of client services, whether you want to pick up IP traffic, you maybe want to pick up cross-connect type traffic that may be going through, or in any non-Ethernet type services across that infrastructure. So augmenting what you have today with the picture on the left, where you have your router connected into your transponder or Muxponder, where you're providing those dedicated wavelength services for a particular client, or you may be connected into an OTN cross-connect to be able to deliver those bandwidth services. So certainly what we want to do is to leverage the architecture on the right and to say, hey, look, how can we continue to converge all the different service types across a packet-switched infrastructure? And for that, certainly we're going to leverage some foundational technologies. Private line emulation is one of those techniques that we leverage, and that's been around for a very long time. Early difference here is that we want to ensure that this PLE or this virtual pseudowire is going to be bit transparent and give you the bandwidth guarantees that you need. So for this talk, the focus will be leveraging a PLE, private line emulation, on top of a segment routed infrastructure, and we'll cover that in a little bit more detail. So when we think about private line emulation, certainly, and we think about the use case, the premise of our talk today, which is really to deliver high bandwidth services in a bit transparent way, private line services, essentially what we want to do is to be able to take in any type of bit stream on the left side and be able to play out that bit stream on the right side. To do that, we'll leverage an EVPN, virtual private wire service. That's a pseudo-wire connectivity to connect both endpoints. What we'll do, we'll look at the bits coming in on the input port, and we'll basically encapsulate those packets into a structure-agnostic payload, making sure that we have a timestamp within that payload, and making sure we also have a control word that we'll see will come in value, we'll discuss later in terms of value of that. But all this is done over packet infrastructure, whether it be running circuit style segment routing, to give you the bandwidth guarantees that we'll need to discuss further on. So as you look at the picture here, we have an incoming bit stream. Certainly we'll do a timestamp on that bit stream. That timestamp will become important as we play out on the other side because we leverage a differential clock recovery mechanism. And we also need to leverage a reference clock on the infrastructure so we can figure out what was the ingress timing to make sure we have some synchronization on the egress as we play out the packets on the right side. So therefore, that implies that there will be a dejitter buffer as well that you'll take advantage of in terms of playing out the packets or the bit stream on the far end. The key point to note here is that here we're saying, hey, look, we can take any different types of services, whether it be SONET, whether it be OTN or Ethernet or fiber channel, because we're really focusing on that bit transparency to get that connection across through the infrastructure. And certainly, yeah, we talked about that, the synchronization from a timing perspective. So what are the various payload types that you'd have with this architecture? Certainly we can go from 1 gig to 10 gig, I mean, as defined. And certainly, I think from standards and papers that's been written, there is definitions to go beyond 2 and 400 gig as you think about the future with 800 gig connections coming down the pike. Certainly, you can see the evolution of the technology moving forward. From an OTN data rates, you have ODU 0 all the way up to ODU 4. And then also from an Ethernet point of view, 1 to 100 gig, and all the various fiber channel data rates that you see there on the chart. So when we think about this emulation environment, the purpose of this view graph here is to say, hey, look, we can mix environments. So you can have a pseudo-wire, a connection that's originating in a packet domain and maybe terminating in an OTN domain. And also, if you're in an OTN domain, you may have, let's say, an ODU2 that you're extracting from an ODU4 structure, if you will, and then be able to extend that connection. What's critical here is really more, as you think about, let's say, that architecture, is to be able to have the right level of telemetry and also the right level of alarming across the network infrastructure. So we leverage a structure agnostic attachment circuits to represent for the various port types, if you will. And essentially what we can have is really the mix of both environments. So from a definition in terms of the working PLE architecture, there's just one environment that you may come across. So you may be having your OTN infrastructure, and you may want to extend your services into your packet infrastructure. So when we think about these environments, certainly failure, how we handle failure, that's a subject of discussion, and that may be on some of your minds in terms of what do we do differently, and how do we make sure that we have the right level of alarming and the right level of telemetry across the infrastructure to ensure that the service is available and the service is there and up. So typically what we've shown here is really an OTN environment where if you had a loss of signal, as an example, there's be an OPU, which would basically have a loss of signal on the client. Then you'd have a client signal fail being propagated to the far end where you can generate a local fault. And certainly you have a notification being able to send across the infrastructure. Here from a PLE or private line emulation, and my apologies, there is some writing in here. So it's this PLE type circuit. The colors didn't come through. The idea is that if you have a local fault on a client failure, what we'll do is actually set the L bit in that control frame, the control word that's in the structure agnostic encapsulation to indicate to the far end that there is a failure, so we can generate a local fault on the far end side of that PLE circuit. So essentially, giving you the same behavioral characteristics that you would have in an OTN switched infrastructure. Similarly, if there's a failure, here we're looking at OTN again, if there's a failure in the OTN domain and there's a failure, let's say, on a span between two nodes, certainly you'd have a loss of signal that would generate an ODU AIS, alarm indication signal, and certainly that will generate a local fault, and there'll be some kind of backward defect indication being propagated through on the far end to notify all the various components about the failure within the network. What we do from a PLE perspective, very similar. if there's a failure in the network. And certainly what we'll generate is a packet loss of signal after some predetermined amount of time. So you'd expect to have a certain amount of packets arriving at that particular node. We'll declare a PLOS, and that PLOS will actually set an R bit to propagate back to the other side, basically acting as that backward defect indication signal, if you will, to notify the reverse end that there was a failure in the network, and also you will have the local failure on that end where you can generate the local fault. So the whole goal there was to say, hey, look, when you look at PLE and you look at the OTN switched environment, what we try to do, or we have done, is actually ensure that you have the right sort of propagation from a telemetry point of view for you to understand fault on the client and also fault within the infrastructure, and be able to treat those differently. And certainly if you have two different environments that are interconnected together, that's going to be critically important as you're generating the right level of messages on either side. My apologies, there's some missed shading on this picture here. But when we think about emulation driving the need for bandwidth commitment, what we're doing differently here is that with emulation, we're making sure we're a bit transparent, but not only that, we're making sure that there's constant network load on the infrastructure. So therefore, we reserve the bandwidth on the network infrastructure, as compared to your normal packet transport, where basically bandwidth is only consumed if you're sending a packet. So if a packet arrived, then you drop the packet, and you'll see some variability within the core of the network infrastructure if you're connecting, let's say, two 10 gig interfaces. Similar with TDM, you'd have a time slot reserved, and you're constantly using that particular time slot. If you think about your emulation environment, you're kind of doing something similar, where you're making sure you reserve that bandwidth, and there's a constant bit stream that's being propagated across that pseudo wire, across that circuit or that connection. So this is just to say, from a technology point of view, and this is not necessarily about implementation, is just to say, hey, look, there's multiple use cases, right? There may be PLE endpoints that sits in that has a pseudo wire. They're sitting both in the packet domain. We talked about before where you can have a PLE endpoint in the packet domain and the OTN domain, and it could be where you have a PLE circuit between two OTN endpoints within two OTN domains, and that's something that's defined. So what are some common misconceptions? Resiliency would be one of those things that people talk about. Does PLE offer protection, protection switching capabilities? I'd say yes, we do. And you also have additional protection capabilities to deal with double failures within the network, as an example. From a transparency, yes, PLE is bit transparent. Latency, no more latency than you would have within an OTN network going through those OTN cross connects. Router latencies are low today, and you can pick the right router platform if you really want to optimize the latency even more. So if you think of, let's say, a pizza box with a single sock system on chip, maybe the lowest latency as compared to, let's say, a modular switching infrastructure. And certainly there's OM&P capabilities, and there's liveness in terms of being able to measure the circuit availability. And there's certainly lots of tool sets for automation and be able to manage the infrastructure. So what we've done so far, we've talked about, we defined what PLE is. We talked about how we could deliver that. We talked about some of the things we need in terms of private line emulation. One of the things that we want to focus on is really how do we deliver that private line service leveraging circuit style segment routing. So there's other talks around leveraging MPLS with RSVP-TE in terms of traffic engineering within MPLS. But here we want to be able to use segment routing and take advantage of the capabilities that segment routing provides. Certainly simple operation and the idea of not having to maintain a lot of state within the network infrastructure. So if we take a look back again at TDM and we look at what we would do if we're building this dedicated service, we'd have a working path, and we'd have a protect path. We'd have a series of cross connects where we cross connect the circuit or working circuit all the way through the network infrastructure, and we'll also have our backup path as well, and we'd have the time slots allocated for the particular circuit that we're set up. So therefore, there's always a working path and a protect path. So if your working path fails, then you move over to your protect path. Similarly, what we do in this packet world is actually build a protected path, just the same as you would have had in an OTN type environment. So you have a path protected, co-routed bidirectional set of LSPs. So therefore, your transmit and receive bidirectional path on your working side, and there's also a protect side. Key here is that what we do, because there's no cross connect to be stitched, what we do is bandwidth reservation along those paths, and we specifically, explicitly state the path itself in terms of what path that traffic is going to be flowing over. So in case there's a failure within the network, we're going to have deterministic behavior and deterministic performance and a deterministic set of service delivered. So on the notion of determinism, when we think about IP networks, there's always these various protection schemes that may be there, right? It would be MPLS with traffic engineering with using fast reroute, or you may be looking at SR with loop-free alternate. With both of these two, the first two as an example, if there's a failure, right, let's say in the first one in MPLSFR, if there's a failure, we route around that link, if you will, but there's no bandwidth allocated and there's no bandwidth guarantee that's maintained. With a loop-free alternate, we may fail over to a path that's give us the shortest path to the destination that we're going to. The key point here is that when we compare that with the path protection, what we have is a pre-allocated working and a pre-allocated protect. If there's a failure, any failure on the working path, we're going to switch the traffic to the protect path, right? So we're not going to say let's fail around on that that link like the two protection mechanisms that was listed above. We're really going to have this deterministic behavior. So you're always going to the path that was pre-set up, predefined for you because that has all the bandwidth guarantees that's there. So essentially mimicking the capability that you would have had within an OTN type of infrastructure. So fundamentally, to be able to provide this, we talked about this before. We're in this implementation, we're looking at circuit style segment routing. It has a set of attributes that's critically important in terms of being able to deliver the capability we're talking about. First of all, it would be end-to-end path protection and restoration, and we'll go through that. We want to have strict bandwidth commitment. Again, we say we want to have dedicated service, right? We also want to have path OAM. So we have all the telemetry on the path that we need to understand the path availability, path liveness, and everything else. We also want to have traffic engineered path, and we want to make sure it's bidirectional, co-routed, and it's persistent. So when we think about this, and this is, I'm sure there's not all of us are IP savvy or not, but this is a quick view of what's here. Certainly what we want to be able to do is to build a path-protected, co-routed bidirectional LSP within this SR domain. So essentially, if I'm going from A to Z, there'll be an SR policy, and in this definition, what we'd see, we want to have a working path and a protect path. Certainly what we're going to have is a working LSP path and a protect LSP path. So if you see here, there's a list of two candidate paths, right? There's a candidate path that we're going to use for working, and the candidate path that we're going to lose for or protect. Typically, if we weren't looking at this dedicated type of a connection, we would have picked the best, pick the highest candidate path and install that. But because we want to have a working and a protect, certainly we have two candidate paths, and we also want to make sure that there's a forward SID list, a segment ID list, and a reverse SID list as well, so we can predetermine the path that we're going to be carrying across the network infrastructure. So that sets up our working and protect. Just to highlight that point a little bit further, because we want it to be deterministic, within segment routing, we have the ability to define the set of segments that we want to be able to use across the infrastructure. And as you see here, we see a SID list here with 150A1, 50, 15, 12, and this is really defining that segment that you're going to be traversing. By having the SID list is actually saying, this is a path I expect you to take at all times, right? So therefore, that's defined. So therefore, no ECMP capabilities. So if there's a failure, don't try to find me an equal cost multipath route, if you will. But the idea is that you'd have a predetermined SID list that gives you the capability that you're looking for. And no traffic rerouting that you'd want outside of what what you've defined. So candidate path connectivity, we also have the ability to measure the path, measure the latency on the path. So that when we define the SID list, we use a TWAM protocol, two-way, I forgot the M and the P protocol, basically to kind of determine the path liveness, the loss delay capability. So essentially what we do, we have this loopback probe, if you will, that defines the forward path and the reverse path. So we're measuring the end-to-end capability of that particular circuit across the infrastructure. So we have these probes that goes across to measure the end-to-end behavior. So what we want to have is a persistent behavior within the network. I'm sure you've seen that theme being echoed in the talk so far. So in a classic behavior, if we had classic traffic engineering behavior, if we had a failure on a particular spanner or link, we'll simply route around that failure, if you will, via a new working LSP. What we want to do is really in this transparent expectation or this PLE type service, we want to be able to not have to do this route around on a link failure, but really move to the protect LSP at all times. So here we had shown a working and protect. There was a failure on a span. We simply say, hey, look, that span fails. There's an alternate path. We can do that. We don't necessarily need to go instantiate the protect LSP there. But in the context of private line emulation services, what we always want to do is to give you that UPSR-like behavior for those of you who are sonnet heads. So what's unique with this PLE service, and some interesting and some really cool things that we can do from a protection point of view. Here we're showing that there's a double failure within the network. So in a case of a double failure, what we have is the ability to make sure that we can signal across the network and be able to instantiate that service through an alternate path within the network. Typically, you wouldn't find that in a UPSR implementation or something along those lines if you're thinking, let's say, comparing, let's say, to like a sonnet type architecture, if you will. So what we have is the ability to have 1 + 1 + R, like a restore LSP, if you will. Key point to note is that restore LSP is not something that's pre-provisioned. The bandwidth is not carved out ahead of time, so therefore you wouldn't have triple the bandwidth reservation. But it's a case that says if there's a double failure in the network and we want to make sure that we have the service be available, we have the ability to go instantiate that third LSP, if you will, and be able to do the reservation at that point in time to give you the bandwidth commitment you need across the infrastructure. So essentially what you'd have is a third candidate LSP that would be leveraged in case there's a double failure within the network, and that gets instantiated or signaled the commitments gets done in event of a double failure, so you don't necessarily overcommitting your resources within the transport infrastructure. That's fantastic, right? So improvement on the protection capabilities within the network. So what we have also is the notion, and there's some lines missing here, is just to say, hey, look, if you have your topology, there would be a PCE controller, if you will, that basically has the full topology view. It has all the bandwidth, the path constraints. So it has a knowledge of the infrastructure. It's the bookkeeper of the infrastructure. Understand all the policies. So therefore, when you set up your SR policies, certainly the PCE would be your friend in terms of ensuring that you have the capability. In the example where we have that third circuit, if you will, your PCE would be that engine that would compute that path and be able to instantiate those set of LSPs to be able to give you the path through the infrastructure. So the PCE, as I said before, has all the topology views. Certainly, when you think about SR and you're playing around with SR, you can certainly go manually define a set of SIDs and SID lists, if you will. But in this case, where we're looking at delivering these services, certainly we want to leverage a controller and leverage a compute engine. So what we just did there was look at briefly some capabilities within circuit style segment routing, certainly some of the cool protection capabilities that's there. So if you have a double failure within the network, you have the ability to be able to instantiate a third or tertiary path through the infrastructure to get making sure that your service is available. And we look at the notion of probing on the infrastructure to make sure our services are lively, our services are available. And we also look at just different protection mechanisms and architectures within the domain. So just to wrap up, certainly putting everything into perspective, certainly with SR, you have all the cool capabilities. You can deliver an Ethernet virtual private wire services today, leverage EVPN, no special hardware is needed, it's very cost effective, if you will. No bandwidth consumption during the idle. So if you kind of think about the 3 states that we had before, where essentially if you deliver an Ethernet private wire service, you consume the bandwidth on the network infrastructure when you need to. And essentially the key ingredients that we'd need there would be ECMP, TILFA, and just scale within the infrastructure and leveraging the simplicity of SR. Complement to that is circuit style segment routing. And what does that give us? It gives us the guaranteed bandwidth. It gives us the persistency, the co-routed bidirectional path. Give us the one-for-one end-to-end protection and restoration within the network infrastructure. And then it allows us to deliver the PLE service, which is really focusing on bit transparency, where you basically can have any one of your protocols running through that infrastructure. And we kind of talked about a few. Certainly, you can support your provider-dependent sync key capabilities, multi-protocol, supporting any kind of connection, whether it be a TDM connection across that infrastructure, an OTN switch to an OTN switch. Typically, you want to reduce the number of those, or you have your fiber channel connections, and certainly flexibility from an MTU limits perspective. So these are the core ingredients of what you would need to be able to deliver on the private line wavelength services delivered another way. You need the infrastructure, you need the routing infrastructure, you need the control plane that's there that has the capabilities, and certainly you need the endpoints that has the ability to be able to take the ingress bit stream and be able to propagate across the infrastructure. One thing to note here, though, is that if you think about your Ethernet private wire service, you can leverage circuit style SR if you wanted to give a customer a dedicated 10 gig where the customer says, you know what, I want the equivalent of what I used to have before across an OTN switch. I want this dedicated pipe carved out for me. All you need to do is just leverage circuit style SR for that Ethernet service. If the customer is looking for something cheaper and you don't want to be reserving bandwidth across the infrastructure, then you leverage the transport capabilities, the capabilities of SR, whether you do SR MPLS or SR V6. So we didn't really specify what implementation of SR you need to use here, but certainly these are capabilities that are there. So with that, I thank you for allowing me the opportunity to speak with you, and hopefully this talk sparks some ideas in terms of what you may want to do with your own network infrastructure. So one thing to note, this is not Cisco specific. There's a whole bunch of standards, so therefore there's drafts for PLE, and there's also drafts for all the stuff we talked about. So I'll encourage you to read those drafts. There's a draft for Schmutzler, and there's all these other RFC drafts that are out there as well. And failure to capture that at the end of the presentation. Thank you.